introduce myself or whether I'm supposed to wait for someone to introduce me, but why don't we get going? So I'm Jim Larus. I work in Microsoft Research. I lead the Software Productivity Tools group, and today I'm going to be talking about some work that we've done in my group and inside the larger organization inside Microsoft Research called PPRC to build tools to improve software development at Microsoft. I apologize in advance that this is a very broad talk. I'm going to talk about a lot of work, and so I'm not going to have time to get into the technical details of any of it, but I'll be happy to talk to you after this session's over if you want to know more. And we have a website which has all of these papers up online. So let me start by motivating why we're doing this. If you look at software development in Microsoft or in the academic world or pretty much at any company, you see that people are using a set of tools that have been around for a while. There are full-screen editors. I think that's Emacs. There are integrated development environments like Visual Studio. There are source-level debuggers like the one that comes with Visual Studio. There are source code control systems. And then there are a couple other tools that people tend to use to bug databases and so forth. And the common thing that all of these tools have is that they're old. Most of them came around from about 1975 or 1980. You can find the original papers, and in fact, in many cases you can find the original versions of these that was in somebody's PhD thesis or something around that era. And that's a long time ago. And it's maybe not for this audience, but sometimes when I give it, the tools are older than the people in the audience, and they're certainly older than most of the developers at Microsoft. And the interesting thing is that the world has changed since then. That was the world of time sharing. And many of these tools became possible when we moved from card decks to time-sharing systems. And so we were looking at machines like that when we built these tools. And we're now looking at quite a different world than we were then. So I just went back and found out how fast the fastest PDP-10 was. So, it was a 30 megahertz machine. The big ones had 4 megabytes of main memory. They had about a half a gigabyte disk on them. And remember, this was a time-sharing machine for about 50 users, and is about as powerful as your cell phone is today. So we're obviously in quite a different world today, and the real question is, why are we using tools that came out of that world for writing software in the world we're in today? And the other way to look at it, the other way we've thought about this is, what goes on a developer's machine when they're doing development? And so here's a histogram, sort of time of day, percent utilization. I'll tell you these numbers are all made up, but they're fairly accurate, I think, in terms of representing an idea, which is what's going on. We have sort of 3 different types of bars here. So the tall bars are really easy, compiling, where basically you set off your machine to compile your program, and you're using pretty much close to 100% of the machine. Your disks are running, and you can set off several compiles to run simultaneously. You can keep the machine busy. The other bars are debugging. You're sitting there, you're thinking, you run your program, you think, you run your program, you think. You're using a fairly good fraction of the machine to execute your program. But the really interesting one is the low bars, when the machine is sitting there idle, which is when you're programming. All the machine is doing is pushing around some bits on the screen and occasionally writing a file to disk. But the machine is really not doing anything. And I would argue that this is the part of the task of a developer that is the most difficult. This is the part where the errors come about. And the question is why we're not using the computing resources that we have available more effectively for making programming better. So the idea would be to get those bars up. Get them up to closer to 100% when the programmer is really doing the most difficult part of their job. And that's what this talk is about, building tools for using the computers to help programmers. So the real idea here is we're not planning to replace programmers. We're not arguing that developers or even testers can be replaced by machines. Instead, we see these as tools that can amplify the effort that developers and testers put in by doing things that people are just not particularly good at, like managing large amounts of detailed information, finding inconsistencies in millions of lines of code, ensuring a uniform level of quality across that millions of lines of code. So that's what we really see tools as being good for, rather than this idea of automated program or even program verification, the ideas that have been around for a while. So what this talk is going to talk about is 3 generations of tools that have come out of PPRC, which is the Programmer Productivity Research Center, which is a combination of a research group and Microsoft's internal tools group. All of it is part of Microsoft Research as a whole. So for convenience sake, I'm going to label these things as 3 different generations because they share characteristics, and I'll explain it in terms of generations. So the original tools that came out and were deployed inside Microsoft are tools called Prefix and Prefast, which are scalable tools. They're heuristic tools. They don't actually have any sound basis. The tools that came out of my research group are sound tools, and I'll explain what that means in the next couple slides. They're based on declarative information, and the examples I'll talk about are 3 of them. And then I'll talk a little bit about where we're going in the future, which is tools that are targeted at particular problems rather than tools that are fairly generic. And just to give you a picture, so here's Microsoft Research. Inside Microsoft Research is PPRC, which is the internal tools group for developers inside Microsoft. And inside there is SBT, which is the research group that I lead, which develops new tools and new ideas. Okay, so let's step back and let me try to sum up what's in common between all these tools to give you at least a mental model of what we're doing. So the big gap we see is that we have programmers who know what they want to implement, and there's a long way between an idea in your head and the actual code you need to write. And that gap is where a lot of the errors occur, that you basically don't get it all right when you sit down to write the code to bridge that gap. So tools can help by having programmers not only supply the actual code that they're going to run on the machine, but some description of what that code is supposed to do, which for convenience I'll just call a rule rather than a specification. And the tools can ensure the consistency between what the programmer's intent is as expressed in a rule or specification and what the code is that they actually write. And the way they do that is they check for consistency between the rule and the code. And if they're consistent, you just basically say, yes, these 2 things do the same. And if they're inconsistent, you point out the inconsistency to the programmer and you leave them to figure out whether the mistake was in writing the rule or writing the code. Typically, it's in writing the rule initially, and then after you've got the rule debugged, you can find the errors in the code. So the types of errors that we look for range from things like language usages, things that are found by many compilers, things like uninitialized variables, null dereferences, to more interesting usages. So, for instance, the programming interfaces that Microsoft has. There are a lot of interfaces where there are rules. So, for instance, you can't close files twice, or they return error results that really should not be ignored in well-written code. You're not allowed to hold a lock forever. You eventually have to release the resource. We're starting to look for errors which are sort of higher-level semantic errors, for instance, deadlock in programs. What we're not trying to look for are what used to be called program verification. We're not trying to look at a piece of code and tell you that this piece of code is correct in the sense of having a very strong notion of what the code is supposed to compute and being able to verify that the code always produces the result that you expect. That's much more ambitious than what we're looking for. You should really think of it as we're looking for errors in the code rather than looking to show that the code is actually correct. We don't really know how to do this in general for large pieces of code. So the approach that I'm going to talk about today, and there are other tools, so for instance the session before they were talking about the testing tools that have come out of PPRC, but I'm going to concentrate on tools for static program analysis. And the idea of static program analysis, as most of you are probably familiar with, is that the tool can explore all possible executions of the program. It's a complement to runtime checking. Neither one is superior to the other one in the sense that static program analysis is extremely complete. We can examine all possible execution paths through the program, but we're not as precise. We don't know as much about each possible execution path. On the other hand, testing is extremely precise. For each path that you execute, you know exactly what the state of the program is going to be. But on the other hand, you can only execute a small number of the paths in the program, and you may miss many of them, and so you won't know whether there's an error along them. Another problem we found is that the analyses for static to explore the programs only exist for a few properties in the program. So there are many things we would like to be able to verify that we don't actually know how to do statically. And so you're going to need testing for that. So the other problem which is worth pointing out is that you have a choice in analysis. You can have sound program analysis where you find all the instances of an error in a program. Or you can have complete program analysis, which doesn't report any false errors, but may miss some real errors in the program. On the other hand, in general, you can't have both. and this comes back to the Turing halting problem, is that if we could actually do sound and complete analysis in general, we would be able to solve problems that we can prove equivalent to the Turing halting problem. And so we don't do that. We have to make a choice. And the choice is at most one. It turns out that you can build perfectly useful tools that have neither property, and I'll talk about some of them today. So you don't actually need sound or complete analysis, but you get some advantages if you choose to use sound analysis, which I'll talk about as well. So let me just give you an example to make this a little more concrete. So here's a little bit of code. There's a file. In this conditional statement, we open the file. In this other conditional statement, we close the file. And the question is, does this piece of code execute correctly? And correctly means you don't try to close a file that's not open, and you don't try to leave a file open that you've opened previously. So there are several paths you can take to the program. You can go straight through, or you can take either conditional. And if we just go straight through and don't execute either body of the either conditional statement, the code is fine. There's no error in it. On the other hand, if we go through and execute both bodies of the conditional statement, obviously the code is again correct. But if we go through and, for instance, open the file and then forget to close it, that's no good. So how do we decide this statically? And as this example should drive home, we really can't, because these predicates could be any calculation that we want. And in general, we're not going to be able to examine two arbitrary pieces of code. Those of you who are standing in the back, there are plenty of seats up here if you want to come up and sit down. So in general, these can be any pieces of code that you want, any predicates, any calculations you want. And so we'd have to be able to decide that this piece of code is equivalent to this piece of code under all possible executions of the program, which we can't do. So this illustrates the limitation of static program analysis. We just cannot be as precise as we'd always like to be. So in something like this, we would have to, unless we knew something about these two predicates, for instance, they could be identical, in which case we would know exactly what happened. But in general, we might have to point out a possibility of an error here. And it might be that the error never occurred and the programmer knew it because they knew something about the semantics of the program that we didn't know in the tool. And in which case, we would be reporting what's called a false positive, an error that doesn't really occur and the programmer would have to ignore. Okay, so now let me just proceed on and start talking about some of the tools that Microsoft has built. I'll start by talking about what I'll call the first generation of tools, the tools prefix and prefast. In sort of quick summary, these two tools really span the spectrum. Prefix is a very detailed interprocedural analysis tool that examines specific paths through a very large code base. It uses a very heuristic, unsound method. It's extremely expensive to run, but is extremely effective at finding bugs in programs. And I'll talk a little bit about that in some further slides. Prefast, on the other hand, is a very lightweight framework for building tools. It was based on the work that Daniel did on the AST toolkit. And the idea here is that you give programmers a representation of their program as an AST, an abstract syntax tree, and they write plugins that walk over the abstract syntax tree looking for particular idioms or properties that are errors. The interesting thing is that we have used these tools very universally throughout Microsoft, and the one number that we've made public so far is that 1/6 of the bugs that were fixed on the Windows 2003 server were found by one or another of these two tools. And that's actually a huge impact in terms of Microsoft if you think about the number of developers and the number of testers that are involved in the Windows product. So let me talk about these in a little more detail. So prefix is a tool for finding errors in C and C++ code. It's really oriented at fairly generic errors, language usage errors. It knows something about some of the Microsoft APIs. Let me defer the questions to the end and answer them all at the end. The tools it looks for are fairly generic. It knows a little bit about Microsoft APIs, but it's really looking for programming errors in C and C++ code. So it's very good at null pointer, memory allocation, uninitialized variable type errors. It knows about some of the APIs, so it knows that they return error codes and that you need to check the error codes. The interesting characteristics about it is that it's interprocedural. So that's a real challenge when you talk about doing an interprocedural analysis of something as large as Windows, which is millions and millions of lines of code. And the way it does an extremely efficient traversal of the call graph. It analyzes the program to find a call graph, and then it does a bottom-up topological traversal where it visits a callee before it visits its callers. Each routine, it examines a limited number of paths. The default is 100. They're very cleverly chosen to give you pretty good coverage of the function, even if it has many more paths. And it builds a model of the function. And then at the call side of the function, it uses the model. And it's an expensive computation, as I mentioned. Windows, even on a fairly large server, takes about 4 days to run. So it's a batch computation that's run in the background. The tool itself has a huge amount of effort and engineering effort to minimize the number of false positives. There's a lot of effort to allow the developers to filter the errors. There's a lot of them prioritize errors. And the reason for this is if you analyze very large code bases on any kind of tool that has a reasonable number of false positives in it, you're going to get back a large number of spurious errors. And if these overwhelm the programmer, they'll never see the real errors. And the other thing that was done inside Prefast is that the heuristics that it uses are tuned to minimize the amount of false positives it finds, even at the expense of missing some real errors. So it gives you no guarantee that it's found all the errors in your program, but it's very effective at finding errors. Let me just illustrate its approach using a simple example. So here's a function with some code, and here's how Prefix would look at it. So it would look at one path, and it would realize there are variables along it. When it saw a usage of one of the variables, it would ask whether it's initialized. It doesn't really know since that's a parameter, so we're going to make two assumptions. Along this path, we're going to assume it's initialized, and it's 0. So we'll go in and execute the body here. We'll see an assignment there. And when we return the value, we'll say it's initialized because along that path it is. The other path, of course, we see the variables again, and we ask whether it's initialized. We don't know, so let's assume it is. But we'll assume the value is not 0 in this case, so we don't execute the body of the conditional. So when we come down here, Prefix will have found an error and reported an uninitialized variable along this particular path. And since it's path sensitive, it can actually point out to the program exactly how it found this error, the path it took through the statements in the program, and give you back a very usable error message, almost like a debugger would. And at the same time as it's analyzing this function, it's also built up a model of it which says that it expects to see an argument that's initialized in this function, and moreover that it returns the value from the function. So that when it sees a call on this function from some other point in the program, it doesn't go back and reanalyze the function. Instead, it uses the model. Okay, so the other tool that really complements Prefast, excuse me, I always confuse the two. The names are terrible. That really complements Prefix is this tool Prefast, which is more of a framework than an actual tool. It's used. It's the front end from the Visual Studio C++ compiler with a wrapper around it to provide a very nice interface to the abstract syntax trees that the compiler builds. Developers write plugins that traverse the trees. There's actually a very large library of plugins that are available with inside Microsoft. It's the basis for building lots more sophisticated tools. We actually use it inside my group to build the tools that I'll talk about later in this talk. But in general, and used inside Microsoft to build fairly simple, fairly low-cost tools that analyze functions by functions locally so that there's very low cost to running this tool. The heuristics that are used are fairly simple. In a lot of cases, what you're looking for is an idiom that indicates that there's an incorrect error in the program. Its big advantages are this fact that it runs very fast on programs, so developers can run it on their desktop as opposed to running it on the server. And it's easily extensible, so that it's built up a very large community within inside Microsoft that's comfortable at using and extending it. So an example, one of the examples I took from the Prefast website is, what's wrong with this code? Anybody have any idea? So if you ran Prefast on it, what it would tell you is that there could be a leak in this code. So this pointer here, P1, which is allocated for new, suppose that this new threw an exception because we ran out of memory after we did the first allocation. You would leave this function, let's say, and this pointer would still be pointing to this block of code new that you previously allocated. Might look like a small error, but if you were writing server code that was supposed to run without leakages for a long time, this would be a problem. So you really should write it this way, which is obviously pretty ugly and a pretty good argument for garbage collected languages. So another use for this with inside Microsoft has been an effort which is called spec strings, which is addressing the obvious buffer overrun problems that Microsoft and everybody else faces. What happens here is that we've tried to build tools to find buffer overruns. It's extremely hard to do in C and C++ because it's difficult to know how long a buffer is. What we've observed, though, is that the code that manipulates strings or other buffers inside C and C++ typically has another variable in the program that contains the length of it, or you know the length of it when you allocate it. And we need to be able to associate the length of a buffer with the actual memory array itself. And so we've gone through and we've annotated many of the Microsoft APIs with annotations like this. So this is a Windows 32 function right here. It takes two parameters. There's the return buffer, which is a pointer to a wide string, and then there's the size of the return buffer, which is passed in by whoever calls this function. And this annotation in red is what's been added, and it basically says that this buffer here, its size is found in this other variable there. So we didn't know that. The programmer knew this, but they had no way of saying it before these annotations. And so a bunch of tools have been built on top of prefast to use this information to analyze code like this. So for instance, here we allocate a buffer with size 20, and we call that function and pass in the parameter 50. And we basically told it that the buffer is a lot bigger than it really is, and so we're trying to read, and it would cause a stack overflow. And this is the actual error message you would get back from prefast. This tool has been used now pretty widely with inside many groups in Microsoft and has found a very large number of potential buffer overruns. It doesn't find all of them. As I said, it's heuristic, it's not sound, but it finds a large number of them, and it finds them very quickly at low cost. Okay. As I said, this is going to be a real quick tour. So now, we're going to now step from the tools that are in widespread deployment to the next generation of tools that have been developed with inside research. And these tools are an attempt to move the development of errors a little further along. And the key characteristics that would distinguish them are that the tools are sound. So the key thing there is that we actually find all the instances of the error we're looking for. So if the tool comes back and says, there's no error of this type in your code, you can rest assured that that error will not occur, which we couldn't do with the first generation. And the other thing is that they're declarative, so that if you want to go and look for a particular property, you write down a description in the textual form of what you're looking for, instead of going in and doing programming like you would do in prefast, say. And I'll give you a bunch of examples of what these descriptions look like in the talk. Okay. So the first tool, the original one that came out of my group, is the tool called SLAM, which is a software model checker. And what SLAM is it takes C code and it takes descriptions of how to use a particular Microsoft API. We've mainly focused on applying SLAM to finding errors in device drivers. So this is the code that's loaded inside with the Windows kernel for all the hardware that you have. They tend to be fairly small, so they've been a great vehicle for doing research. There's a lot of them. There's literally tens of thousands of device drivers for Windows. So when we build this tool, we have lots of things to run it on. And they have lots of errors. They actually cause somewhere around 40 or 50% of the blue screens in older versions of Windows. And so it's important to find these errors. So we've been applying it to that. The tool is actually more general than this, but we've mainly talked about this in terms of drivers. The way it works is it examines the C program and builds an abstract model of it in a language called Boolean programs, which is just C without any data types except Booleans. And then it explores the model's state space using model checking. And it asks the question whether there's a path in this model that leads to an error. If there is, we ask the question of whether the path is feasible. And if it is, we found an error. If not, we found a false positive. If the false positive, we do a refinement of the model. We say, is this error due to the fact that the model is too coarse? If it is, we go back and come back with a better model. So let me make this a little more concrete by talking about the specifications and then giving you an example. So here's a simple state machine. Oops, the blue lines don't look too good on blue. Apologize. You can have a lock that's unlocked. If you acquire it, it goes into the lock state. If you release it, it goes in the unlocked state. If you do the wrong thing, it goes into the error state. And the way we would write it in the language called SLIC, which is the specification language, is basically say it has two states. It starts off unlocked in the kernel, you acquire a spin lock by calling this function, and so if it's locked, it's an error. Otherwise, if it's unlocked, it becomes locked. And similarly for releasing a spin lock inside the kernel. So this allows us to associate the state transitions with particular function calls in the kernel, and it gives us the semantics of a lock. And what we want to do is we want to avoid calling this abort. So the way that SLAM works is that you take a program and a specification, which is in the form of the SLIC rules, and you give it to a tool SLIC, which takes the rules and literally sticks them into the program. So when you see a call on acquire lock, we stick in the code that you saw in the previous slide for acquiring a lock. And we get a program P prime, which we feed to SLAM itself. Now, SLAM has three major subparts in it. There's C to BP, which translates the C code into a Boolean program, which we feed to our model checker, bebop, which can say there are no errors in the code, in which case we're all done. And we can tell the programmer there are no errors in your program. More likely, what we're going to find out is that there is an error in the program. There's some path that leads us to one of the abort statements in the program. And so we take the path and we feed it to Newton. And what Newton does is it asks the question, is this path feasible in the original C program, not in the model of the program, but in the original program? And we use a theorem prover to decide the feasibility of a particular path. If the path is feasible, we found a bug, and we can give it to the programmer, and we can say this path leads you to an error state in your program, and we can give you some information from the theorem prover about that path as well. More typically, what we find out is, at least initially, is that the path is not feasible. It was an artifact of the fact that our model was too crude. So we feed the predicates from the path back to the C to BP, which produces a more refined model of the program, and we use that to iterate through the model checking process again. And you have to go through this a number of times. In practice, we find for even real drivers and real properties, the number of times we go through it is between no more than about 10 to 20 in general. So it converges pretty fast. All right, let me make this a little more concrete by giving you an example. So here's some code from an actual Windows device driver. And the question is this code correct? Does it obey the locking rule that I put up on the earlier slide? And the answer is you don't know yet. So first thing that SLAM does is it strips away all the incidental computation and comes up with the simplest Boolean model, which is just the control flow graph of the program. We keep the locks and releases of the spin lock there, but we don't really have any control information about the program. And then we feed this to the model checker, bebop, and what it does is it systematically explores the paths through the program. That first path where we go through and we don't actually execute the if statement here and then fall out of the while loop, we acquired and released, so the lock is dealt with correctly. If we take the other path where we actually go through the conditional statement over here, what we find out is that if we fall out of the loop, we have two releases along the same path, and so we violated the rule that we wrote down earlier. So it looks like there's an error in the program, but remember, this is an error in the model of the program so far. So we asked the question, is this program really feasible in the is this path really feasible in the original program? And the answer is, well, we have these other statements in the program, these statements in blue, which are manipulating these variables n packets old and n packets. And the path is actually not feasible in the original program. And the theorem prover will find a contradiction. And moreover, it will give us this predicate n packets old equal to n packets, which we label with in the program with the Boolean variable b, which is initially true, and then here where we change one of the arguments to the predicate, if it was true, it becomes false, and if it wasn't true originally, we don't know what it is now, and then this is just not be down here. And so what we've done is we basically examined the path. We've come up with the fact that it wasn't feasible, and we are able to use that to refine the model. So this is the second Boolean program. The code in green is what we've added to the original model of the Boolean program. And we now take this model and feed it to the model checker, which knows about Boolean variables. And along the first path, B is true along the whole path, and so everything is fine. But along the second path, what we see is that when we get to the statement here, it was originally true, so it becomes not true at this point. And we're in a while loop, and since this is not true, we aren't going to fall out of the while loop. We're going to go back here. And so the path that the model checker found to be non-feasible, when we refine the model, it's also not feasible in the refined model of the program. And so this is the way in which we build up a better and better model of the program. And it turns out that if you keep on this process, you'll find out that the original code was actually correct, that there was no places where we violated the state machine rules. So SLAM has been turned into a tool called SDV for Static Driver Verifier, which research is co-developing with a fairly large group in Windows now. It's been deployed with inside Microsoft for developers' use and may be released someday to driver writers outside Microsoft. These numbers are a little out of date. We've applied it probably closer to 200 drivers. The number of rules is closer to 40 or 50 than 13, and the number of bugs is in the hundreds now. So it actually finds real errors in real code. Some of these drivers are 50 to about 75,000 lines of code long, and we can run it routinely, and Windows is actually very excited about deploying this tool to find bugs inside Windows device drivers. Okay. So this is one end of the spectrum. Remember, I said device drivers are fairly small. We're talking, 50 to 70 to 100,000 lines of code. The biggest device drivers that are in existence are only 1 million lines of code. Suppose you really wanted to apply this process to very large code bases, something like Windows, tens of millions of lines of code, Office, tens of millions of lines of code, or some other programs that size. How do you do it? And so another project that was done within my group called ESP is an attempt to trade precision for scalability. The idea is that SLAM was very focused on reducing the number of false positives, giving you back very high quality results. But suppose we really want scalability rather than precision. And what ESP does is it uses more conventional program analysis techniques. Instead of using software model checking, it's based on techniques that come out of the compiler community, such as whole program value flow analysis and path-sensitive alias analysis. It's very similar to SLAM in the sense that the properties we're looking for are describable by state machines. But the difference is that the analysis technique is just totally different once we go to the implementation. So let me explain ESP in terms of talking about it from the point of view of somebody trying to build an analysis. And how do we examine a large number of paths to a very large program? Most of you probably have the intuition that the number of paths grows exponentially with the size of the program, or can grow exponentially with the size of the program. How do you deal with this in terms of millions of lines of code? We can't follow each path throughout an entire program and analyze it separately, so we need some sort of approximations. And the question is, how can we introduce approximations that don't cause us to lose a lot of errors in doing the program analysis? Again, we're going to start with a finite state automata to describe the rule. Along each path, we're going to track the automata, and we're going to track some part of the program state. And the problem comes with deciding what part of the program state we can afford to track, because as the program goes larger, the amount of state that we have to track grows larger. And this becomes most obvious at branches. So when a program splits control flow at a branch, we have to investigate both branches of the program, and we have to track the state along both branches. And when control flow comes back together, we have to decide what to do. If we maintain both states of the program independently, the amount of information that we have to track can grow quite quickly, can grow, in fact, exponentially. It's easy to construct programs that cause that to happen. On the other hand, if we don't track enough information, if we go back to the standard techniques that are used in compilers of doing data flow analysis, we're going to lose a lot of information, and we aren't going to be able to accurately report errors. So the problem is, in data flow information, they only track the finite state automatas. They don't actually track the state of the program. And so when control flow rejoins it in a program, we have to merge the states so we have a single value which represents all the paths that led to that point. And that's unfortunate because, as this example will show, it doesn't give us enough precision to report errors in general. So this is a state machine for, I think this is a file, so it's opened. Originally it's closed. If you open it, it goes into state open. You can read it. If you try to open it twice, it's an error. If you try to close it when it's closed, it's an error. If you try to do anything when it's in an error state, it's an error. So this is another simple state machine that comes up all the time in analyzing programs. And here's some code very similar to the code I showed you for SLAM. We have some conditionals that are governing the operations. And the question is this state machine correctly followed by this piece of code? And if we analyze it, we go and we see a control flow graph, and the key points are these points at which the control comes back together, the green points right there. And so if we analyze it using a data flow analysis point of view, we see two paths to the first statement, one of which opens the file and the other one doesn't. And so when the control comes back together at this particular point, we don't know whether the file has been opened or not unless we can track the individual paths, which we've decided not to do because we're doing flow analysis. And so all we can say is the file could be either opened or closed, which is fine at that point. But later on, when we get down here and we see the other closed statement, we unfortunately don't know whether we actually have an error or not, because if the file wasn't opened and we try to close it, it is an error. So we need more information. We can't just use the approach that's been used in compilers quite successfully. We actually have to track some part of the program state, not just a finite state automata state. And the question of exactly what we have to track is when the branches in the program actually determine the transitions and the rules, we should track the state of the program that determines the branch. That's a little hard to decide, and in fact, we don't really know how to do it in general. So the heuristic that ESP uses is that it tracks the program state when the finite state automata that we're interested in moves into two different states along the arms of the conditional. And so if we go along both arms of the conditional and it doesn't affect the finite state machine, or both of them move it into the same state, then we basically don't track the program state along those two paths. And as you'll see in this example, it actually, let me see the examples next. It actually works quite well. So here's the same code expanded out a little bit. So what happens here? So originally the file's closed, and if we take the first path, the dump variable is true, and we open the file, and so we track the fact that the file is opened and the program state that took us along that path is that dump equals true. If we track the other state path through this conditional, dump is false and the state of the file is closed. And so we have seen the state machine move into two different paths along the two different states along the two different paths. And so we don't actually merge this information together. We maintain it as two separate pieces of information. We then come down and look at the next conditional through the program. Let's take this value first, and we propagate it through this conditional, and nothing really changes. The state of the finite state automata is opened. We have a little more program state, and similarly, if we come along this path, we have the state of the finite state automata is opened, and we have more program state, which is slightly different. But from our point of view, the difference of the program state, whether x is 0 or 1, is irrelevant to us. It really doesn't tell us anything useful because we're really only interested in tracking the file. And so at this point, we merge these together and throw away the program state that varied and go back to the program state that actually influenced the variable we're interested in tracking. And similarly for the other value, we propagate it through here. And so you can see what's happened here is that this conditional really doesn't affect the file, so we don't track the information across it. This is one of the ways in which we reduce the amount of information we need to propagate through the program. So down here, we come to another conditional where it actually matters. We have some information. Dump is true, so that this can only go along this path. The state was opened and now it's closed, so it comes down here and gets closed. And similarly, the other value comes down here, and we only go along this path because dump is false, and we end up down here. And the other thing we can do at this point is that we can merge these together. We can throw away the information about the program state because it really didn't affect the state that the file ended up at this particular point in the program. So the key thing is we're very aggressive at merging state together that we have to track in the program and discarding it as soon as possible. The idea here is to avoid the cost of the exponential blow up along different paths while doing the path sensitive analysis where it's actually valuable for tracking different information in the program. And the belief is that there's a slide missing there. the belief is that we can actually do this across millions of lines of code. We've applied this now to some fairly large pieces of code, not tens of millions of lines, but small numbers of millions of lines of code. It seems to work pretty well. There are certainly circumstances in which the heuristics don't actually produce the best possible results, and we're working on applying this to programs and improving the heuristics. It's found this technique and this tool have found real errors in real programs and are now being developed inside Microsoft Research, inside PPRC, into an internal tool for the rest of the company to use, scheduled for deployment pretty soon, I think. Okay, so let me now change gears and talk about a different way of doing this. So the tools I've talked about now have basically said the programming languages are fixed, they're out there, they're C and C++, and the specifications are separate from the programs, so that they're sitting, in a separate specification language and typically in separate files written by separate people. Suppose that you looked in the future. You might think that it would be better to actually bring these specifications into the programs themselves rather than leaving them out there, which requires us to change the programming languages. So we've also done work on new programming languages. There was a language in my group called Vault, which actually was an attempt to build a better version of C where we could write code that was safe yet didn't require garbage collection and was compatible with C code. Many of the ideas evolved into a tool called Fugue, which takes the best features of Vault and makes them available to code running in the managed environment inside the CLR. And so the basic idea here is that there are many specifications we would like to make part of the program. For instance, can this method return a null value? Who owns a resource? Who has the obligation to free up this resource? Do I have to call the methods on a class in a particular order? Are there invariants on data in the program? And we would like to make this part of the API itself, part of the program code itself, so that tools can be built to use it. So currently what we have are things like this, comments. So this is the format that you have inside the Visual Studio environment for specifying comments on APIs. So here we have a get page function which takes in a string argument and returns a string. And you can see that there's some semi-English text here which describes what's going on, and it can be extracted and formatted very nicely into manual pages. But it's really intended to be human readable and is actually fairly imprecise. So what we've done is we've turned this into what are called attributes in the CLR world. So these things in square brackets are part of all the languages in the CLR, C#, Visual Basic, the managed C and C++ worlds. They're not understood by the compiler. They're literally taken from the source code and put into the assemblies, the managed code files that are there as uninterpreted metadata. And then we can build tools to actually read these assemblies, read the metadata, read the bytecodes, and compare these specifications against what's actually in the code. And as I'll show you later on, there's a big advantage in doing it at the bytecode level as opposed to doing it at the language level. So what this says is that this function returns a result that is not null, and moreover, the argument that it takes we expect to be not null as well. So this is the basic process. So for Fugue, we have a C# program with source code, and it's fed into the regular C# compiler. Our annotations that we put in there, the language that we've designed to write these specifications, is not understood by the compiler. This is the standard unmodified compiler. These attributes are just passed into the assembly metadata file. And then we have a tool down here called Fugue, the Fugue checker, which reads in the metadata, and there's actually a repository where you can write these specifications for files you don't own, such as the standard .NET libraries, and then it produces error messages here. I said there's an advantage to doing this. This information, in particular the metadata and the assemblies, are language independent. And so the tool that we built doesn't just work for C#, it actually works for all of the languages. So we were very pleased when we built this, and we actually went back and we wrote the attributes in a Visual Basic program, and we ran it through, and our checker worked just as well on Visual Basic, a language that we know nothing about, that we've never programmed in before, as it did in C#, the language we actually would prefer to program in. And so we found this to be a huge advantage, to actually be able to deal with it at this level and not have to deal with the peculiarities and the syntax of a particular program. So let me tell you a little bit about some of the kinds of things that we can do with Fugue. So the idea here is that these specifications that were on the previous slide express a contract. And the contract is a contract across the interface to this particular function. So a client that calls this function is checked against the contract. So for instance here, if we wrote some code which did a get environment for a home page variable, well, this can sometimes return null if there's no environment variable there. And so we have the string here, we pass it in, and Fugue would tell you that this string can sometimes be null because we have annotations on this particular method in this class here, which say that it sometimes returns null. And so we can track that information. But we also can track the contract on the other side, on the implementation side. So for here we have the interface decorated that way, and suppose we had the code for get page, and there was a path through this code which returned a null result. We could detect that path, and we could point out that the contract says that the result should be non-null, and you're returning along a particular path a null result. So again, we can track the contract on both sides, the implementation and the client as well. We also have a way of writing down the rules similar to the state machines previously. So here's the socket interface, which is similar to the BSD socket interface. Very complicated set of functions you've got to call in the right order. If you write them down as a state machine, they look like this. If you write them down as Fugue code, they look like this. And this, basically says here's a socket. It can be in one of these four states: raw, bound, connected, or down. When you create it, this function socket creates a new socket. It returns in state raw. When you call bind, the socket you call it on better be in state raw, and it comes out in bound. And similarly for the other annotations here. And so when you give us a piece of code that uses the socket interface, we can track the values, track the state of the values, and point out the place where you called the wrong function at the wrong time. Fugue is a type checker. We view the process that it goes through as an extended version of type checking for behavioral types. So it has many of the advantages of type checking. In particular, it's extremely cheap to run. It's applied to one method at a time in a compiler, and it's fast enough that we could visualize it. We can envision it being made part of a compiler and made part of the process that you run on every single time you compile a program. And we're hoping to get to that stage someday. Okay. Let me briefly mention some of the work that we're working on currently on what we'll call the third generation of tools. And the idea here is that the tools I talked about previously were focused on general purpose programming problems, things that could be described as errors that almost anybody could be add to the program, either language errors or API usage errors. We're now looking at more specific types of problems that require maybe application of the previous tools, maybe new techniques. In particular, the two that are the biggest issues for Microsoft are obviously security, and we're also looking at concurrency because that seems to be the direction the world is going in, and it's a well-known difficult area to do programming in. We're also looking at combining static program analysis and runtime analysis, trying to build on the strengths of both of them. We believe that the combination could be better than either one individually. We're looking to apply new program analysis techniques, in particular theorem proving and SAT solvers, to these problems. We believe that these can bring in many strengths that the existing tools don't already have. So let me just briefly mention one of the things that's going on in my group in conjunction with some of the researchers in Cambridge. So this is a project called Behave, which is looking at web services, which is an area that many of you may be familiar with. There's a talk at 4 o'clock on it as well. And so the idea here is that there's a distributed system where I have a machine that's just talking to a website which provides functionality for my program. And the question is, how do we check across this interface? This is in many ways similar to the problem that Fugue tries to deal with, where we have a contract between a client and a server. And so we'd like to be able to write this down. The new twist here is obviously concurrency. These two machines, this may be a concurrent website, these two machines are certainly concurrent. The interfaces that websites provide in many cases are concurrent. You can allow several things to be going on at the same time. And so what Fugue has done is basically show that we can check the properties by writing them down as rules in an extended version of state machines that allow concurrency. We can check the client against the rules. We can check the implementation against the rules. And moreover, a very strong property that we proved is that if both the client conforms to the rules and the server conforms to the rules, the system as a whole is stuck free. So it's basically deadlock free, a generalization of deadlock free. It also, neither one will send a message to the other one that they're not expecting to receive. So you can always make forward progress in the system. And that's in spite of the fact that we're never checking the client code against the server code or vice versa. We can check each one individually against the contract. So that's just a preview of where we're going in terms of the work we're doing. I only have a couple more minutes, so let me step back a little bit and try to describe some of the lessons from the tools that have been built inside Microsoft Research. One of the interesting things is that how well heuristics suffice for building tools. We didn't actually start off with this as a belief, but what we found is that many developers, many testers are very happy to have a tool that will find bugs. The soundness, the ability to find all the bugs is just an additional benefit, but if the tool is effective in finding bugs, you can make a lot of people very happy. Another interesting thing is that the user interface in many cases is more crucial than the underlying technology. In particular, when you present somebody with 50,000 possible bugs in a very large code base, you better give them a very good user interface or they're just going to stop using the tool very fast. Another insight is that the developers who use these tools are extremely rational. There was a lot of resistance to these tools initially because they looked at the tools and they said, we don't really expect them to work. We expect to spend a lot of time and get very little benefit. And as the tools became more popular and became more successful, the perceived cost-benefit trade-off changed, and the tools were a lot more widely adopted a lot faster. And so the question the developers are always asking is, do I expect this tool really to benefit me, or do I expect it to be a net time sink? And if you can convince them that it's going to be beneficial, you can almost always get somebody to try a tool. Another interesting thing is that the simple tools, the ones I talked about at the beginning, paved the way for much more sophisticated tools. There's been a huge change in attitude in Microsoft in the past 5 years in terms of tools. When I got started, everybody told me Microsoft developers will never use tools. Microsoft developers will never write specifications. That's no longer true. Developers not only use tools, but they want better tools. They want tools to solve their problems. They're happy to write down specifications if they think that it actually will benefit them. And that's been a really big change. Another thing is that as the tools get deployed, the simple bugs get fixed. Things like things that prefast can find. Those things get routinely fixed. They get kept out of the code by running the tool over and over again. And so it exposes more complicated, more interesting bugs. And so the tools have to evolve as the simple bugs get eliminated. So in general, tools can improve the program development process. They find significant numbers of bugs and significant bugs as well inside very large code bases. There's the potential with the sound tools that are just starting to be used to eliminate entire classes of bugs, entire types of bugs in the code base. And I see this as a new way of programming that, currently the tools are fairly crude, fairly inaccurate, but we're starting to apply computing power to aid programmers in building better software and systematically building better software. We can already see the improvement inside Microsoft in terms of the developer and tester productivity. And as more and more tools become widely available, we're going to see more benefits to Microsoft and to other companies as these start to systematically find bugs and eliminate bugs from the software. And really, this can lead to better software. This is something that's been talked about for a long time. But we're actually now starting to see this happen inside real code bases inside Microsoft. So let me just put up a couple URLs. We have papers galore on the website. And I think I have about 5 minutes for questions, so right back there.
Okay. Lots of questions, although I'll just stick to the two that I was going to ask earlier. The first is a value of the tool is not so much after the fact in this case, but what provides feedback to modify programmer behavior or the coding environment so that those bugs can't occur in the future rather than have to find them post facto. And the other question I wanted to ask you is figure of, you found 1/6 of the bugs, and that's rather interesting because 1/6 of what? 1/6 of all the ones found by tools? No. 1/6 all the ones found by beta?
Okay, let me answer your second question first because it's easy. 1/6 of the bugs that were fixed in the development process. So there's a bug database and basically...
Prior to release?
Prior to release.
Okay.
Yeah. So, the ones that were closed as fixed, 1/6 of them were found by tools.
So the ones that got out, despite all the methods, those are the really interesting ones.
Yes, and the question, of course, is why they got out. Did the tools know about them or did they not know about them? There haven't been so many yet that we have any evidence one way or the other. I mean, 2003 has only been out for a month or two, so I can't answer that question. Going back to your first question, that's actually an interesting point, is, do these tools make a difference in developers? And the answer, sort of anecdotally, is yes. And let me give you a sort of an interesting data point. So I mentioned these two tools, prefix and prefast. So prefix is this batch tool that runs and throws a bunch of bugs into the bug database where everybody can see them. Prefast is this tool that runs on developer desktops, and they run it before they ever check the code and anybody else sees it. Guess which tool is a lot more popular with inside the company? Prefast. Developers really like to be able to fix their bugs before anybody else can see them. And it's considered a bad thing to have prefast find bugs and throw them into the bug database, particularly if it finds the same bug over and over again in your code. So yes, there is definitely a training effect. But, people are imperfect. People make mistakes. And many of these things are just very hard things to find without tools. That's why I put up that example from prefast with the 2 calls on new. That's the kind of code, nobody, unless you're really attuned to it, are going to think about. And it really helps to have a tool to sort of back you up and find that kind of error and point it out to you. So, yeah, we haven't actually done any real experiments to sort of measure whether developers stop making mistakes if it's pointed out to them. But anecdotally, it seems to be true that developers find these useful and actually apply them. With me.
So, any plans to share infrastructure, binary source tools with the community?
Yeah, there's definitely talk about that. I can't talk about any particular plans because I'm not sure the answer is very clear even with inside Microsoft. Certainly the Phoenix infrastructure, which is the other talk that's going on right opposite this one, you would be able to build many of these tools on top of Phoenix. And in fact, when Phoenix gets to a more mature state, we will probably port many of our tools. Some of these other tools have been transitioned into Visual Studio and will be introduced as products at some point in the future as well. So it's not just Microsoft, but it started with inside Microsoft. Yes?
Jim, those annotations in Fugue, just from a testing point of view, I'd love to have those.
Yeah.
Is there any prospect of that actually becoming part of a coding standard?
We're working on it with inside Microsoft. We're still at the stage where we're trying to convince people with inside Microsoft that this is worth doing. And I would like to tell you that, yeah, everybody believes that right away, but we're still at the stage of having to demonstrate it. And so it's not in a coding standard. We're working on it, and hopefully before some libraries get released, it'll actually be put into the libraries. But I can't make any commitments. One last question.
About buffer overflows in the first generation tool.
Yes.
Did you see a sound tool for buffer overflows?
We tried really hard. A number of years ago, before the huge security push and everything else, we sat down and looked at buffer overflows really hard and tried to apply many of the program analysis techniques we had. And what we decided is that there were just so many ways you could mess up with C and C++ that we couldn't see a single tool that would find it. It turns out that this insight that the information is almost always available in some other part of the program, in some other variable, was the key one to building a pretty good heuristic tool. But in terms of sound program analysis, we just didn't see one that would find a large number of buffer overruns, and so we never built it. And as a consequence, we can't get rid of all the buffer overruns in our code or anybody else's code. So, well, that's it. Thank you very much.